Today we begin by introducing decision trees in Python through Telecom, Churn, and Titanic datasets. Decision trees in Python, ID3, C4.5, CART, Telecom, Churn, and Titanic. Welcome! In this hands-on lesson, we will explore how decision trees work for real-world data mining tasks. We will use the Telecom, Customer, Churn, and Titanic datasets. By the end, you will be able to build, understand, and evaluate your own decision tree models. Let us get started. Running the cell now. Think about one prediction problem you might want to solve as we go. We will start by turning off warning messages so that our output remains clean and easy to read. We import warnings so our notebook can control warning messages. Import numpy as np. We set the random seed to 42 for reproducibility. We tell Python not to display any warnings from here on. This step keeps the notebook less cluttered while learning. Running the cell now. Here, we set a random seed and suppress warnings to ensure consistent results and a clean output during our decision tree exercises. This setup helps you focus on understanding the model and data without distraction from irrelevant messages. It's an important best practice when working with real-world datasets like Telecom, Churn, and Titanic. Think of one time you have seen a confusing warning in code. How did it make you feel? Let us talk about what a decision tree is. What is a decision tree? A decision tree is a way to make predictions by splitting data into smaller and smaller groups. Picture a set of yes or no questions that lead to a final answer. In data mining, decision trees are used for classification, which means predicting categories, and regression, which means predicting numbers. Running the cell now. Can you think of a time where you or a computer used step-by-step questions to make a decision? Let us load our main dataset to practice decision trees, the Telecom customer churn data. We make sure the notebook is clear about what dataset we are loading. We import pandas to handle our data in tables. The data is loaded directly from an open GitHub link. We read the data into a table called df. We print how many rows and columns are in the data for context. We see the first few examples to understand what each row looks like. Running the cell now. This output shows the Telecom customer churn dataset with 7,043 rows and 21 columns, offering a range of customer information from demographics to service details. Notice how each row represents a customer and key columns like churn indicate whether they left the service. This setup prepares us to use these features in building a decision tree that predicts customer churn by splitting data based on these attributes. What do you notice about the variables in this data preview? Time to clean our data a bit so it is ready for analysis. Basic step: make a copy of the original data to avoid changing it directly. We remove the customer ID column, since it is just an identifier. We make sure the total charges column is stored as a number, preparing it for analysis. We count any missing values just in case the data did not load cleanly. We print out how many missing values we actually have. If missing data is found, we remove those rows for simplicity. We print out the new shape, which tells us how much data remains after cleaning. Running the cell now. This output shows that after converting the total charges column to numeric, 11 missing values were found and removed, resulting in a clean dataset with 7,032 rows and 20 columns. Notice how this step ensures the data is complete and ready for building an accurate decision tree model. Cleaning the data like this is essential before splitting it based on yes or no questions for classification. Notice how much data is lost just by cleaning. Imagine why it is important to check for missing values. A quick explanation: models need numbers, so let us transform the text data. Turning categorical variables into numbers. Decision trees in Python like numbers, not text. We will convert yes or no columns and other text into ones and zeros. Running the cell now. Think of an example where yes and no might be used in a computer system instead of numbers. We are going to change all columns with text values, like yes or no, into numbers. We start by describing that we will convert text columns to numeric. We go through each column in the data frame one by one. We check if the current column stores text data, object type. We check if the unique values in this column are exactly yes and a no. If so, we convert yes to 1 and no's to 0 for easier model processing. If the column has other text values, we assign a unique number to each distinct text. Finally, we print the first few column data types to verify the changes. Running the cell now. The output shows that all columns, including those originally containing yes/no or other text, have been converted to integer types. This confirms our code successfully turned categorical text into numeric values, which decision trees require for proper processing. Notice the key step, direct mapping for yes/no columns and factorization for others, ensuring all categories become numbers. Try to spot a column in the printout above that is now an integer instead of object type. Now, let us look deeper at how a few features differ between churned and not churned customers. Exploratory Data Analysis, EDA, Preview. Let us take a quick look at a few features most related to churn, the business outcome. This helps us see trends before modeling. Running the cell now. Looking at the data before modeling is always a smart move. We will plot and visualize some important features to see differences between customers who churned and those who did not. We import matplotlib and Seaborn for easy plotting. We set a clean style for all our charts. We apply Seaborn's white grid style for a clean background. We add a comment describing the following box plot comparing monthly charges by churn. We set the figure size to make the plot readable. We create a box plot showing the distribution of monthly charges for each churn category. We add a descriptive title to the box plot. We display the box plot so it appears in the output. We add a comment describing the following count plot showing churn counts. We create a count plot to visualize the number of customers who churned versus those who did not. We add a title for clarity on the count plot. We display the count plot to see the final results. Running the cell now. The box plot reveals that customers who churn tend to have higher monthly charges, highlighting a clear difference in the distribution of charges between churned and retained groups. The count plot shows the overall number of customers who churned versus those who stayed, which helps contextualize the scale of churn in the dataset. Together, these visuals provide an early indication that monthly charges may be a key predictor for churn, guiding further analysis and modeling efforts. Where do you see more variation, in monthly charges or churn count? Let us summarize what splitting rules in decision trees mean and why they matter. Decision tree, theory pulse. Decision trees use splitting rules based on the data. Popular ones are: ID3 uses information gain, which is based on a concept called entropy. C4.5 improves ID3, using something called gain ratio. CART uses a Gini index and can be used for both regression and classification. All these methods create tree-like models that are easy for humans to read and explain. Running the cell now. Have you heard the word entropy before? In data science, it just means uncertainty. To measure how well our decision tree works, let us divide the data into train and test pieces. We load a handy function that splits our data for training and testing. We choose churn as the variable to predict. We separate our target labels from the rest of the data. X is our featured data, Y is what we want to predict. Now we split the data into training and testing sets, using 1/4 of the data for tests and a fixed random seed for repeatability. We print how many examples go into training and how many into testing. Running the cell now. The output shows the shapes of the training and testing feature sets after splitting the data, with 5,274 rows for training and 1,758 rows for testing, each containing 19 features. This confirms that 25% of the data is reserved for evaluating the decision tree model, ensuring we can assess its performance on unseen data. Noticing the consistent feature count is crucial for maintaining model integrity during training and testing. Why do you think we set data aside for testing? Let us build a simple cart decision tree classifier now. We import the decision tree classifier from scikit-learn. We create a tree using the Gini split rule, which is the default for cart. Limiting depth keeps our model simple and helps prevent overfitting. We train the model, meaning we use the training data to find splitting rules. We print out performance on training examples. We also print how well the model does on test data to check generalization. Running the cell now. This output shows the training and test accuracy of a cart decision tree using the Gini impurity as its splitting criterion. Notice the reasonably close accuracy values, around 78%, which indicate the model generalizes well without overfitting. This illustrates how cart can effectively create splits to capture patterns in data, aligning with the lesson's focus on practical tree building methods beyond entropy-based splits. Try changing max_depth and see how it impacts test accuracy. Decision trees can be shown as diagrams, which is helpful for beginners. We import a plotting tool just for decision trees. We set up the size of our figure so the text is readable. We plot our tree up to 3 layers deep to keep things clear. Showing class names like no and yes makes the tree easy for humans to read. We display the chart which shows how the model splits the data. Running the cell now. The output displays a visual representation of the first 3 levels of a cart decision tree, highlighting how the data is split based on key features to classify the target variable. Notice the filled nodes indicate class purity, illustrating how the tree segments data using binary splits, a central idea in understanding how decision trees make predictions. This visualization helps connect the theoretical splitting rules, like entropy or gain ratio, to the practical structure of the tree. Follow a branch from the top to see how a typical decision is made. With our predictions ready, we examine detailed evaluation results. This comment indicates we will generate a confusion matrix and classification report next. We import the functions needed to evaluate our model's predictions. We use our trained decision tree to predict the target variable on the test dataset. We print a header to indicate the confusion matrix will be shown. We display the confusion matrix, which summarizes the performance of the model in terms of correct and incorrect predictions. We print a header to indicate the classification report will be shown. We print the classification report, which provides detailed metrics such as precision, recall, and F1 score for each class. Running the cell now. This confusion matrix and classification report show how the decision tree, cart, performed on the test set, with more correct predictions for class 0, true negatives and true positives in the top left and bottom right. Notice the imbalance, higher precision and recall for class 0 compared to class 1, indicating the tree is better at identifying the majority class. This highlights the importance of evaluating splits and metrics beyond accuracy to improve decision tree performance on imbalanced data. What do you notice about the number of false positives or false negatives? Let us build an ID3 tree that uses the entropy rule instead of Gini. We build a second tree, but now using entropy as our splitting rule. We keep the depth the same for a fair comparison. We train this new tree just as before. We print how well ID3 does on training examples. We print the test set performance to compare with previous results. Running the cell now. This output shows the accuracy of a decision tree using the ID3 algorithm, which splits data based on entropy to maximize information gain. Notice that the train accuracy, about 79.7%, is slightly higher than the test accuracy, about 78.2%, indicating a good balance between fitting the training data and generalizing to unseen data with a max depth of 4. This confirms that ID3 effectively captures key patterns without overfitting too much at this tree depth. Does entropy make your tree more accurate? Try using a different depth. C4.5 uses similar splits as ID3 but adds extra controls to avoid overfitting. Let us simulate C4.5 style using scikit-learn. We build a third tree with entropy as the splitting measure, like C4.5, plus a rule that requires more samples to split. Adding a minimum sample split is a way to prune trees and avoid making overly specific branches. We fit the model as before. Now we print how well our C4.5 inspired model fits the training data. We check its test accuracy as well for a valid comparison. Running the cell now. The output shows the train and test accuracy of a decision tree using entropy-based splitting with pruning parameters, max depth and minimum samples per split, to control complexity. Notice that the train accuracy, 79.7%, is slightly higher than test accuracy, 78.2%, indicating the model generalizes well without overfitting. This connects directly to the lesson intent of illustrating how C4.5 style pruning improves model performance by balancing fit and complexity. Why do you think adding minute_samples_split can help reduce overfitting? Let us peek at which features matter most to our decision tree model. We provide a comment about what this code block does, which is showing feature importance for the tree model. We load NumPy for working with lists of numbers easily. We grab importance values assigned to each feature by the decision tree. We sort features by their importance, showing the most meaningful ones first. We select the top 5 important columns for simple output. We pull those feature names. Now we list the names of our most impactful data features. We loop to print out both the name and score of each important feature in order. Running the cell now. This output reveals the top 5 features that the cart decision tree found most important for making splits, with contracts contributing over half of the total importance. Notice how contract type strongly influences predictions, far more than other features like monthly charges or tenure. This highlights how decision trees select key attributes based on their ability to reduce impurity, aligning with the lesson's focus on informed splitting rules. Does the list match what you expected based on business intuition? Ready for a class mini project? Let us switch gears to the classic Titanic dataset. Mini project, try the Titanic dataset. Now, let us predict survival on the Titanic using what we have learned. This will help you see if your skills work across more than one problem. Running the cell now. Want more exercises like this? Hit subscribe on our YouTube channel to get new scenarios each week. Let us load the Titanic dataset with pandas and peek at its columns. We begin by indicating the start of the data setup section for the Titanic dataset. We import pandas, a library for data manipulation and analysis. We define the URL where the Titanic dataset CSV file is hosted publicly. We read the CSV file from the URL into a data frame named df2. We print the shape of df2 to see the number of rows and columns. We print the first 3 rows of df2 to inspect a sample of the data. Running the cell now. The output shows the Titanic dataset with 891 rows and 12 columns, confirming we've successfully loaded the data. The preview reveals key features like passenger ID, survived, our target variable, P-class, sex, age, and fare, which we'll use to explore patterns and build survival predictions. This initial check ensures we understand the dataset structure before applying the skills learned to solve the survival prediction task. What columns do you think will most impact survival? We pick key columns, fill missing values, and turn text into numbers so the tree can use them. Prepare Titanic data for decision trees by selecting relevant columns. Keep only the important columns related to survival prediction. Fill missing values in age with the median age from the dataset. Replace missing embark values with BES, the most common port. Convert sex from text to numeric values, 0 for male, 1 for female. Convert embarked categorical values into numeric codes for the model. Running the cell now. Here, the code prepares the Titanic dataset for modeling by selecting key features and handling missing values, such as filling missing ages with the median and missing embarkation points with the most common port. It also converts categorical variables like sex and embarked into numeric codes, which is essential for decision tree algorithms to process the data. Notice how this cleaning and encoding step sets up the dataset in a consistent format, ready for training a predictive model. If you had to pick just one column to predict survival, which would you try? Let us make a basic decision tree to predict survival, then see how well it does. We use the same method to split data into training and testing groups. We import the train_test_split function to split data for training and evaluation. We remove the survived column from df2 to create the feature set x2. We extract that survived column as the target variable y2. We split the data into training and test sets, keeping 25% for testing for fair evaluation. We create a decision tree classifier with a max depth of 3 for interpretability. We train the decision tree using the training features and labels. We print the accuracy of the trained tree on the training data. We print the accuracy of the trained tree on the test data, which it hasn't seen before. Running the cell now. The output shows the model's performance predicting Titanic survival, with about 83% accuracy on training data and 80% on test data. Notice the similar scores, indicating the tree with max depth 3 generalizes fairly well without overfitting. This demonstrates how a simple decision tree can effectively capture patterns to predict survival based on the features used. How does this accuracy compare to random guessing on the Titanic problem? Now it is your turn. Pretend you are a passenger, enter your details, and see if the tree predicts survival. This line is a comment telling you we will ask for your prediction inputs interactively. We ask for the passenger class, which means first, second, or third class. Next, enter gender as a number, with 0 for male and 1 for female. We prompt for age, which can be a decimal for any age group. You will input family details, siblings or spouses aboard. We also ask for parents or children with the passenger. Fare is your ticket price but can be any number, so enter what you like. We convert port to a number, 0 means Southampton, 1 means Cherbourg, 2 means Queenstown. Now we bundle up your answers into a row that our model understands. The model makes its prediction just for your invented passenger. We print out if your sample was predicted to survive or not. Running the cell now. The output shows the model's prediction based on the specific passenger details you entered, here indicating the person did not survive, 0. Notice how this interactive code uses the same features from the Titanic dataset, like class, sex, and age, to apply your trained decision tree and make a survival prediction. This reinforces your ability to generalize and use the model on new, custom inputs beyond the training data. Try out a few pretend profiles and see what changes. Enter 1, 0, 30, 1, 0, 50, 0 for a typical first-class male. Here are a few tricks to keep your results trustworthy and helpful. Best practices and troubleshooting tips. 1. Always check if there are missing values after you load data. 2. Visualize features to look for outliers or surprises. 3. Set random_state in train_test_split for stable results. 4. Try different max_depth, minute_samples_split, and split criteria. 5. Avoid leaking the answer in your features. If your tree overfits, prune it or require more samples at each branch. Running the cell now. Which one of these will you try first? A few bonus exercises if you want to level up your tree modeling skills. Extra decision tree challenges. Challenge 1. Tune your tree's depth and report a test score. Challenge 2. Use feature_importances_ to pick the top 3 variables and build a mini-tree. Challenge 3. Try predicting a friend's survival on Titanic using your tree. Bonus, show your plot as a tree diagram and try explaining a branch in plain language. Running the cell now. Share your results in the comments on our YouTube video. Let us look back at the ground we covered so you remember the key steps. Recap, what did we learn? What decision trees are and why they are great for beginners. The difference between ID3, C4.5, and CART. How to clean, prepare, and split data in pandas. How to fit and evaluate trees in scikit-learn. How to read feature importance and explain results. Congratulations, you have now built and interpreted your own decision trees in Python. Running the cell now. Take a moment to write down one thing you want to try on your own dataset now. Before you go, here's how to keep learning and help us grow the channel too. Thanks for joining. Next steps. Keep practicing building decision trees. Try out different datasets or challenges from our playlist. If you like this lesson, give it a like and subscribe to our YouTube channel for more hands-on data mining guides. See you next time. Running the cell now. If you want more fun code by code videos, hit subscribe. See you soon.